Hi everyone, my name is Prayush Kumar. I'm a postdoc at Cornell University, and I work at the interface of waveform modeling and numerical relativity. And I would like to first of all thank the organizers of this conference for having me here, and especially Bala, who has been an inspiration to many of us. So today I wanted to talk, in fact, I wanted to give a brief update on what is the state of the art in binary black hole source modeling, and what are the questions that are still open, and what are the questions that are going to be posed to us in the very near-term future, especially with the upcoming third generation and more future detectors. So this is the problem that this is the system that we are trying to model. It comprises of two black holes and orbiting each other and spiraling under radiation reaction. This system is completely characterized by 8 numbers, the 2 masses of the holes, and the 3-dimensional spin vectors of each of them, as well as kinematic parameters which may describe the shape of the orbit in case the orbits are not quasi-circular, right? So there have been many different approaches for finding solutions to this problem. We already heard a lot about the post-Newtonian approach, which is a perturbative approach. Then Larry talked about how we numerically solve Einstein's equations to evolve this binary black hole system. Then there are other approaches that take the first two approaches results. So the first two approaches give ab initio results, and then there are derivative approaches that take results from these and combine them to present a unified picture for the complete in-spiral merger and ring-down process for the binary black hole systems. So this diagram was also already shown by Guillaume Fay and Ryuichi as well. It shows the binary separation on the y-axis and the ratio of the two masses in the binary on the x-axis. Now, when the objects are far apart, we can approximate the system to be in the weak field slow motion regime, and the motion of the two objects is well approximated by perturbative post-Newtonian results. But as they evolve closer to each other, there comes a point where the perturbative PN results are no longer sufficiently accurate. And to really know the physics in that strong field regime, we have to perform numerical evolutions, completely numerical evolutions, to unravel the full nonlinearities of Einstein's equations, right? And then there are, as I said earlier, there are approaches such as the effective one-body approach and other phenomenological approaches that take results from both these domains and combine them to present a unified picture of the system. So I'm going to go through each of these in turn and present to you what is the current state of the art for them, and then what is missing from each of them and what will be needed in the more long-term future. So first, of course, is PN theory. We already heard a lot about it this morning, so I'm not going to go into much detail. Suffice it to say that from a data analysis or an astrophysical inferencing point of view, post-Newtonian results alone are sufficient to derive astrophysical information for very low mass systems, which spend a long time in spiraling in the band, within the band of gravitational wave detectors, such as mostly double neutron star systems. However, the kind of sources that LIGO is seeing the most frequently these days, which are high mass binary black hole systems, which spend only the last few milliseconds or maybe at most a second within the band of LIGO. Post-Newtonian results are simply not complete enough. They don't have enough information to extract unbiased information from data, right? And the condition gets worse as the mass ratio or the spin of the system, of the holes in the system increases. So for instance, here I'm showing the match between post-Newtonian waveforms as a function of mass ratio and spin on the bigger black hole against a complete in-spiral merger ring-down waveform. And we see that while for small mass ratios and moderate spins, these waveforms agree well. Yes, this is faithfulness, yes. So I'm taking the most stringent requirement for accuracy, which is needed for, say, tests of GR, not for astrophysical PE, for instance. Right. So in the strong field regime, then, we like to perform fully numerical evolutions of Einstein's equations. And because these are expensive, they typically start from about 10 to a few tens of orbits before merger and proceed on to a few cycles after merger, right? And this is the current state of the art that we have in available literature. So numerical simulations used to be quite expensive. In fact, in the last decade, there has been tremendous advancement in numerical technology that have allowed more and more simulations for more and more extreme parameters. So this is reflected in the public catalog of these simulations that have been released over the years. So 10 years, about a decade ago, was the first few catalogs that were released by the Ninja 2 and the NRAR collaborations. These catalogs had relatively short simulations of relatively moderate binary black hole systems. So for instance, most of the simulations here were either non-spinning or had equal spins on both the holes. Similar is the case here. Then as time went on, the catalogs became larger. For instance, the first public catalog released by the SXS collaboration had about 170 simulations. Most of them were, again, small mass ratios, but some of them had larger mass ratios as well as extremal spins. Yeah. Then a few years later, we published yet another catalog of about 90 simulations that again explores the similar region of parameter space. Other groups as well, they made their simulations open source more recently, such as the Georgia Tech group or the RIT group. And this table here, taken from Boyle et al. 2019, summarizes all the open catalogs that have present in current literature at this moment, starting from the earliest to the most recent. And the state of the art is the SXS public catalog, which was released earlier this year. This has about 2,000 numerical simulations. But most of these simulations are for mass ratios below 5, right? And only a small fraction of these simulations have higher mass ratios or very high spins here. For instance, this panel shows the spin magnitude of the two holes. And you see it's densely populated for spin magnitudes below 0.8 and sparsely for spins with higher magnitude. Similarly, the most recent catalog published by the RIT group has the same properties. Again, it's missing simulations with mass ratios below 0.2, which is the same as mass ratios above 5. And so this general state of affairs shows that the current capabilities of numerical relativity across groups is that while we can do lots of simulations of comparable mass ratio binaries, it is not easy or inexpensive enough to perform more extremal simulations quite yet. Right? And then how accurate are these simulations? Well, for advanced LIGO's purposes, these simulations are quite sufficiently accurate. So for instance, this figure here shows the mismatch between a simulation performed at the highest resolution and the second highest resolution for 2,000 simulations that were published as part of this catalog. And there are mass ratios between 1 and 10 here and spins between 0 and up to very close to extremality on both holes here, right? And we see that while the median mismatch is about 0.1%, you can think of most of these simulations to be more accurate than at least 1% in terms of mismatches. Now, in terms of the highest and second highest resolution. So this is a measure of the precision of the simulation. Yes. So typically we have performed studies of, so there'll be errors because of the finite length of the waveforms. There'll be errors because we are extrapolating them from a finite radius out to asymptotic null infinity. All of those error sources are usually comparable or sometimes smaller to these error sources in the studies that we've done in the past. Okay, so this is not to say that a lot of these frontiers have not been breached already. So there have been papers in literature that, for instance, simulate black holes with spins as high as 0.994 or simulate black holes for more than 150, 180 orbits at length, or perform relatively short simulations but of very high mass ratio binaries, right? Such as this simulation was for a 100:1 system. However, these are rare and still quite difficult to do, right? So how the way we go about in practice in using all of this information to extract astrophysics from gravitational wave data is to use hybrid waveform models such as the EOB and Phenom models, right? And EOB is the picture where we take the two-body problem, map it to an effective one-body problem, using post-Newtonian, Hamiltonian in the two-body problem, that gives us the conserved dynamics in the effective one-body picture. And then the energy radiated by the multipoles at null infinity gives us the radiation reaction on that system that allows the orbits to evolve in the effective one-body picture. Now, this model has free parameters both in the conservative as well as radiative parts of the dynamics. And those free parameters are then carefully calibrated to numerical simulations to make sure that the model agrees with numerical results, right? So this is the state of the art in terms of how accurate EOB models are. And this here shows the mismatch between EOB and numerical relativity for a range of total masses and range of mass ratios, spins, etc. And we see that the typical mismatch is about 0.1% and the maximum mismatch is about 1%. So this level of accuracy is quite sufficient for cyclic noise ratios of up to 40 to 50, which is roughly the range that we see with advanced LIGO these days. Another approach is to bypass trying to model the dynamics of the problem and go straight ahead to model the gravitational waves being emitted by the system. This is what is done in the phenomenological approach, where the final waveform is divided into three portions: the early in spiral, the post-merger portion, and an intermediate regime. And a theory-inspired ansatz is taken in each of these regimes. And this ansatz, of course, has several free parameters that are then calibrated to a dense grid of numerical simulations. And by calibration against numerical simulations, this model is able to effectively well capture most of the most of the physics of the problem in terms of the observable signatures, right? So again, state of the art, this line of thought is the Phenom D model, which is the 4th version. And again, it has similar accuracy as with the EOB families. So it is accurate most of times when compared against NI, it is accurate between 0.1 and 1%. So in the interest of time, I'm going to skip ahead a bit and go to the summary of the current status of all the waveform families that we have. So what I wanted to mainly say is that the current waveform families, the best we have, are good up to mass ratios of 6-ish, because that's where they have been calibrated, and up to black hole spin magnitudes of up to 0.8 or so. And their accuracy has come up to approximately the level of how accurate our numerical simulations are. And this is all true for binary black holes in quasi-circular orbits. If you have eccentricity in the orbits, then the picture is quite different. In fact, the state of the art is that only recently we have had the first model that presents a complete in-spiral murder ring-down picture of the eccentric in-spiral, right? And again, this first model does not capture spin effects yet. So there is a lot to explore in this domain. However, so in terms of open questions are again dictated by the kind of sources that we want to see. With LIGO, we want to see black holes with individual masses up to 50 solar masses and mass ratios up to 10. So for LIGO binary black holes, our waveform models can be approximately considered to be sufficiently accurate. But if we move on to another kind of sources, which is the black hole neutron star binaries, which have mass ratios above 5, so the matter effects are not as important, right? And their waveforms will be essentially the same as that of an equivalent binary black hole system. But they can have mass ratios as high as 30. For instance, a 1.4 solar mass neutron star inspiraling into a 40 solar mass black hole. And our current models are nowhere close to being able to model the higher mass ratio end of such systems. So just for LIGO, what we still need from both numerical relativity and waveform modeling community is many more waveforms, much better calibration at higher mass ratios. We need a better modeling of the subdominant harmonics that are present in data. And these subdominant harmonics become increasingly important as we increase the mass ratio as well. So the harder problem is made harder by the importance of these harmonics. And of course, we also need models for spinning plus eccentric systems, for which we have very little information available from either the modeling community or the numerical relativity community so far. This is not to say that performing these simulations is very difficult or impossible, it's just that it has not been done to the sufficient level of detail yet. Going forward, I just want to show a couple of slides on LISA. So as Larry already mentioned, that since for the binary black hole problem, total mass scales out of the problem, most of our waveforms were carry forward for the case of supermassive black hole binary mergers that LISA will see. And these black holes can individually have masses between 10 to the power 5 to 8, which means they can easily have mass ratios above 100, right? And they can, while they're not expected to have very extremal spins, they can still have moderate spins and definitely can have eccentric orbits. So in fact, these supermassive black hole mergers will be the loudest signals in data, and they will stay in band for LISA for hours to days, to maybe a month in band. And the reason we need very accurate waveforms for these is because we want to, first of all, extract as much physics as possible. So we want to be able to test gravity, we want to do parameter estimation properly. But also, to be able to extract information about the lesser loud signals, we need to be able to subtract out the loudest massive binary black hole mergers first. And if we do not have a very good model for those signals, then the residuals alone will interfere with our understanding of any of the lesser loud gravitational waves that are present in data. So the question remains, are our current models, are our numerical waveforms even currently sufficient for seeing and extracting physics out of these supermassive black hole mergers? And while there's no available answer in literature, I found this figure in Deirdre Shoemaker's talk at APS meeting earlier this year, where she's taken a very simple case of an equal mass supermassive black hole binary of total mass 10 to the power 6 solar masses at redshift of about 2, where they take a numerical waveform and prepend it with a phenomenological inspiral. And the total signal to noise ratio in this very realistic signal is about 2,700. And if they've swapped out just the NR part with the simulation at a lower resolution, then and subtract the two waveforms, they find that the signal to noise ratio in just the residuals is already above the noise curve itself, right? And this is the relatively easier case to model. This is an equal mass binary with not very loud spins. So I can only extrapolate that when we go to more realistic supermassive black holes, which will have mass ratios to 10 or higher, then our numerical errors will already be dominant above any other signals that will be present in data. But we definitely need to quantify this better and soon. Okay, so in summary, we need more work for higher mass ratios. For low mass ratios, we will still need better quality waveforms, both from numerical relativity as well as from the modeling community, if we are to attack the problem of supermassive black holes with LISA. And all of this has not even touched upon the case of intermediate mass ratio inspirals, which will either need third order self-force or numerical relativity information to model these systems. That's it.
General questions about the NSBH thing which is going on right now. If we do not have accurate models for NSBH at higher mass ratios, so even if we detect one, will you be able to say confidently without an electromagnetic follow-up that this is an NSBH signal? Because the probability that the mass ratio will be high is more because the source will be most probably distant.
So if we don't have sufficient accuracy within our models, then the mass ratio posterior that we will recover for a hypothetical neutron star black hole system will be fairly broad, right? And which means that the posterior recovered for the smaller object's mass will be equivalently broad. And what's worse is that the same posterior from different waveform models may not significantly overlap with each other. So when we have such little information about the mass of the smaller object, it's hard to place any astrophysical bounds in terms of the nature of the object. Assuming we don't have information in other bands, such as an electromagnetic counterpart. So it will be very hard, and it is very hard at the moment.
So will it be possible to come up with something in short term so that we can confidently claim a detection? If we
Well, that will strictly depend on the mass ratio of the neutron star black hole. I'm talking in the hypothetical scenario when we have mass ratios of 20 or 15 or 10. If you, yeah, Alexander should say more. But if you have lower mass ratios, the picture is different.
I just wanted to add that we should distinguish the detection from the interpretation of the signal. The fact that one, can make a strong a statement that a source was detected may have nothing to do with the interpretation of it. You can still say that you detected a signal, and that, with the template bank that one has is possible because you can mismatch the parameters, but you still can get a very highly significance in your, detection. But then the question is what it is, and one could have, some uncertainty depending on the waveform that one is using, etc. But it's not a question of detection. They can be distinct. Yeah, it could be, but we have to be patient.
Okay, so as you said that we don't have enough waveforms for the eccentric systems, like none of the catalogs. So, and I understood you said that there are not very challenges available, it's just that it's not happening. So as you know that in India, we are already putting efforts to generate the waveforms, but right now it's more on the standard things which have been happening. So what can you suggest and what can you recommend such that we come up with the new waveform bank, which is not being generated by other NR groups?
So the modeling of eccentric orbit, systems in eccentric orbit has recently picked up pace. In fact, in the last 3 years, small catalogs of eccentric waveforms have come up, but all of these catalogs are lacking any spin effects on the black holes. They are all just non-spinning black holes on elliptical orbits in spiraling. So one thing that probably could be done, one frontier that can be approached here is to include the effects of spin. And starting with aligned spin, so we don't have too many new degrees of freedom to model in terms of when you use those simulations to construct an analytical model. And then the next stage, of course, will be the fully generic scenario, which is